We're rolling. Okay, so today, two completely different things again today. So I'm gonna sort of continue on the source of the EEG. I mentioned it last time, but I want to go into a little more detail about EEG signals, electrical signals that you can record from the brain at different scales, because this is a very important thing, the idea of sort of coarse graining, like you have certain things happening at a micro level, but as you move up a level of organization, sometimes you can ignore little stuff going down there and just try to figure out what is the sort of more macro picture. And there's actually kind of three levels that are worth distinguishing there. And then completely changing tack to talk about a little bit of basic math that we need for understanding current source density. So one of the ways of trying to figure out where activity in the brain is doing something called current source density. You can do it in 1D, 2D, or 3D, but in order to understand how that works, we have to go through GradDivCurl quickly. So let's start off with the source of the EEG again. And so we said that the source of the EEG, at least at the scalp level, was due to the fact that we have these anisotropic cables. So we have a neuron here like this, drawn up. We're looking really close on it. So here's a pyramidal neuron, and there's the axon hillock, and then this little thin part of the axon is called the initial segment, and then the axon thickens up a little bit, and then it gets all this myelin on top of it, a whole bunch of layers of myelin. And so the parts. So this guy is called the initial segment. And that's where the spike starts, where this electrical disturbance that essentially transfers the signal down the axon to go someplace else. And so what we said was that, if we look at that in a little more detail, what actually happens when the spike starts is that some sodium channels open up, and a whole bunch of sodium, rushes into the axon right here. But it turns out it's actually relatively hard to directly record that, and the reason is this is quite a small thing. I drew it a little bigger than it is. But if you put an electrode down, so one of the ways at a micro level you can record from the brain is to put a micro electrode in, and so if we draw a micro electrode sort of approximate to scale. So here's the conducting part of the micro electrode, and it usually has an insulator on it, like you could put some glass, for instance. But the glass isn't present at the tip. So this is the insulator. So just the tip is exposed. So if you record here, actually what you see is these ions are going in, and they go down this way. They go down the axon that way, but they also backwash into the dendrite like that. And so if you record with a micro electrode, so this is micro electrode, what do you see? You'll see a spike. And so what does the spike actually look like? Well, if you think about it, the sodium ions are going away from you. They're sort of disappearing into the axon. And so what the spike looks like is the spike will be upside down. So the spike will, this is you normally think of a spike as sort of looking something like this, but the spike will be upside down. Now, if you go inside the cell, if you were to put the electrode inside the cell, then you would see the opposite. Then you would see the spike going positive because of the sodium rushing in. But if you're recording, for the most part, you tend to record sort of outside the cell because it's hard to sort of put the electrode in the cell without damaging it. So the spike is typically upside down like that. But it turns out that if you put this kind of electrode down into the white matter, so remember you've got, like here's the pyramidal cells, and there's all those other types of cells we talked about, and then the axon goes out into the white matter. So here's the white matter, there's the gray matter. If you put the electrode down into the white matter, you won't hear anything. It's completely quiet down there. Now, there's tons of spikes going by, so why can't you hear them? So the reason you can't hear them is that, how do they work? Well, if you have a myelinated axon, there'll be a long distance with myelination, and then the myelin will stop, and there'll be a little exposed piece of membrane like that, and then the myelin will start up again. That's called the node of Ranvier. And there's channels in there. And what is the point of this sodium? The point of the sodium is to depolarize that channel so that some sodium can come in. It'll go both ways again. And that will then go on to the next node. But the problem with this is that what happens is that there's other channels in there. There's like potassium channels. They're right next to the other one, and so the little loops of current are so close to each other that a big electrode like this won't even pick it up. So you can make a tiny little pipette that's about the size of the node of Ranvier, and then that can actually pick up a spike. But so what that indicates is that even in the cortex, this cable structure of the neurons is actually important for recording spikes. And as an example, if you put the electrode up here, so say the electrode happens to be just right here. So here's the insulating part of it. What happens then? I've done this in the past. Back when I was recording from neurons, I would sometimes see a right side up spike. And I would say, well, what's going on there? That can't be. How could it be right side up? There's no way I could be inside the cell, because I would ding the electrode a little bit, and that would like immediately damage the cell, and it was still working. If the electrode was inside the cell and you touched the electrode, just a tiny little vibration of the electrode, it would tear a hole in the cell, and you wouldn't get anything. So what was happening is basically you're just recording when the spike is right side up. You're just recording backwash coming out of the cell. So even for recording spikes, you basically rely on the fact that you've got this sort of cable structure. So that's the micro level. But you might have heard of something. So this is like, you would call this like single unit recording. So if you want to read papers on it, this would be like single unit. They say unit because they're not sure exactly what they're recording. So single unit recording. So it turns out you can't see spikes at all from an EEG electrode on the surface. They all get sort of mushed together, and you can't see any spikes. And like I said, you can't even record spikes with this kind of electrode if you're down in the white matter. So this is the white matter down here. So, but you might have heard of something else called a field potential. So what is a field potential? So a field potential can be recorded from this same kind of electrode. And so if you actually look at the signal coming out of this electrode, what you'll see is there's several different things coming out of the electrode. So if we look at that signal, there'll be these spikes. So here's a spike coming out of the electrode, and maybe here's another spike. It's upside down, but it's riding on top of this large potential. like that. Maybe there's another spike down here. So that's the actual electrical signal. So this is the, electrical, voltage. This is a voltage, coming out of the electrode. So it's got two things in it. It has these very rapid spikes, and so when you see a recording, so when you take something like this, what you can do is you can do what's called a low-pass filter. Well, let's do a high-pass first. So a high-pass just means just let the high frequencies through. So you can do some kind of filter on this time signal. So this is time going this way. So a time domain filter that will essentially get rid of the low frequencies. And in that case, then you see, you just see the spikes. And so often you might see, a paper where they show, spikes happening like that, and they're against a flat baseline. So that's a high pass filter. So that means just see high frequencies. High freak. But you can also do a low pass on the same signal. So here's low pass. So low pass means just see low frequencies. Yeah, just see low. And if you do that, then what you'll see is, you'll just see that low frequency signal. So that signal is in there. And that one, so, this signal is, are called, the spikes. And this signal is generally called the local field potential, or the LFP, sometimes they'll call it the LFP, local field potential. So that's in there too. And what is that? That's the result of all the other cells in the area getting activated in the same place and causing this large amount of sort of backwash and inwash to occur. And so this is the roar of the crowd. This is just whatever cell that you happen to be really close to. You have to be quite close to the cell in order to be able to record a spike. So you'll record just a few cells, but then you'll see the sum total of all the other cell activity, which is essentially what is going to create the EEG on the scalp. So you'll see this signal. That signal is there at the microscopic level, in addition to the spikes. And the way you see it is, you either, do a low pass, either do sort of take this signal, do a low pass, or just take the exact same signal and do a high pass. So that's kind of like the micro level. So when you get to the sort of like mid-level, what's the sort of mid-level, kind of at the level of a cortical area? So it turns out that we can make a little sort of caricature of what the cortical connectivity between different cortical areas looks like. And so so now we're sort of backing out to the size of about, one cortical area, maybe like something that's like about a couple centimeters across. So here we were at a micro level, so the cell body, a large pyramidal neuron might have a cell body that's maybe 20 microns across. That's 1/50th of a millimeter. So, well under a millimeter. Now we're backing out to 10 millimeters for a cortical area. And so when you look at a cortical area, what we see is there's a tendency for cortical areas to have sort of a particular lamination pattern that's pretty common, and we can sort of identify the can identify the, what do they call that one? Oh, original input. Yeah, so there's layer 1, and that's the original input. So if you look at very primitive cortex in something like a turtle, you can see that most of the input used to go up to layer 1. It doesn't have any cells. There's hardly any cells in layer 1. It's almost all just wires with dendrites coming up. But then there's layer 2, 3, and you can think of this one as the feed-forward layer. So this basically projects to the next step along. And layer 4 is the input layer. So that's typically where the input comes. Layer 5 is the motor output layer. So if you look in motor cortex, the neurons that project down to the spinal cord, they come out of layer 5. And then layer 6 is the feedback area. And this is sort of it's not exactly the same in all different areas, but this is kind of a reasonable characterization. And so what happens if you look at something like the dorsal lateral geniculate nucleus, it projects in to the to the input layer, and then if you look at cells in the input layer, they project up to the feed forward layer, and they project to the feedback layer, and so on. And then if you look at the motor output layer, that projects down, so that goes down to, for instance, something like the superior. If we're in visual cortex, it might go to the superior colliculus. That's a motor structure, controls eye movements. And then we've got the feedback layer. If you look at the feedback layer, well, the feedback layer goes back to the geniculate. I'll use that sort of thing like that, like we're making synapses. So that we could call this a lower area. Now, of course, lower and upper are a little bit relative. Lower area, because there's all this feedback to lower areas, and so, so for instance, V1 is a lower area, but it gets input from a lot of higher areas. So there's higher area information in V1, in addition to lower level information. So that's a lower area. And so then if we go to a higher area, we can see that the projections to a higher area will often come from this feed forward layer. And so if we look at how that works, it's going to go now to layer 4 of the higher area. So this is a higher area. Area, for example, V2. And similarly, there's feedback coming from it. So feedback will come out of layer 6, and it will come back and synapse on everything but layer 4. So it'll skip layer 4 and synapse on all the other layers. So it's kind of respecting the fact that layer 4 is the input layer. And you see the same, thing here. So the neurons here will go up to, higher and lower areas, higher and lower layers, and then this will be a higher level motor output layer, and then here's the feedback layer, and then this one will be, go to yet a higher area. So that kind of cartoon of how the cortical areas work roughly holds across the cortex, and so it gives you some idea that, the signals at the level of going between one area and another area are exactly the kind of signals that we can actually record with EEG on the scalp, because the areas are a couple centimeters, 1 or 2 centimeters across, and that's approximately the spatial resolution that we have, that we'll talk about later when we talk about localizing EEG signals. So we are capable of actually detecting these signals going back and forth between different areas, and And this is a good cartoon to sort of remember about, approximately how these different cortical areas are hooked up to each other. So this is all the gray matter. This is, gray matter here. Okay, so now, finally, so that's kind of our mid-level. Finally, let's kind of go all the way up to the macro level. So this is kind of mid. And now all the way up to the macro level. So when we go up to the macro level, we have the skin. So here's the skin. And then there's the skull. Skull is a pretty good insulator. Generally, it's often assumed to be 1/80th as conductive as the brain. So it's like 80 times better insulator. And then we've got the cortex down in here. I'll draw it really big so I can draw some cells in it. It's obviously smaller. And so this is our brain right here. This is our brain. So what's happening there? Well, we've got a cell in the brain, and there's some currents. There's a channel there, and so some positive current is going in there, and then it's kind of leaking out. And then we might have an electrode. So here's an electrode on the skin. And let's put we got another one that's kind of further away. So here's another electrode, so on the skin. So we said this is the reason that we can actually see anything, because there's all these lined up cells. They're stimulated simultaneously at one layer or another. And as a result, you get this macroscopic current flow in the brain that's detectable. And so this is a big resistor, so a tiny bit of current is going to actually get through the skull, out to that electrode. But the skull is a good insulator, and so the current is going to prefer to go, sideways like this. So it's going to say, well, that's a high resistance pathway. I'm going to go through this low resistance pathway. And then, a tiny bit of it is going to come out of here too. And so we said that the reason that you can see the currents at all is because of the fact that you've got these cables. The cables, which means like a good conductor with an insulator around it. You have these cables that are basically the apical dendrites of the pyramidal neurons. But you have like a second order, so there's a higher level, a higher level cable of the skull. So the problem is that, because the skull is such a good insulator, it's going to do something sort of similar to what a pyramidal neuron will do, and it will kind of smear out the signal, and so the currents coming out of this neuron are going to actually, leak out all across the entire scalp, and so virtually any local activity in the brain is going to create a signal on every electrode. So you can see that that's going to make it more difficult. The signal will be a little bigger on this electrode than it will be on this one, but there's going to be a signal on this one too. So that's the macro, yes, the macro picture. And then I mentioned last time when, how do you get MEG? Well, MEG is simply, if you've got a current that's running sort of more or less parallel to the skull, like say, for instance, this guy, that current is going to basically make a magnetic field that sort of goes in this way and comes, it goes out that way and comes in this way. I always got to remember the learning glass. So if we plot the magnetic field, the strength of the magnet, remember the magnetic field is a vector. It's an arrow. And so if we plot that, if we plot just the strength of it, it's going to look like that. So there's going to be arrows sticking out of the head over here, and then there'll be arrows going into the head over here. So this guy right here is the current. So the current is a vector also. The voltage is just a number, but the current is a vector. So that's a current going in some direction, like for instance this direction. And then that creates a magnetic field vector. So the magnetic field vector is going to be sort of sticking out of the head on this side. So that's the B vector. And it's going to be, going into the board. Going into the board on that side. So that's MEG. So MEG is basically, so here's EEG. MEG is just the magnetic field vectors caused by these currents flowing around. And we can either record the currents, the vector currents, as scalar voltages, just numbers coming out of the scalp, or we can record the magnetic field vectors coming out that are due to the same currents. Oh, the sum of all the currents, obviously. Okay, so that's back up to the macro level, which we finished with last time. So as we talk about this, you can begin to see, this is kind of a mess, isn't it? Because I've got a current over here, and that current is going to be creating a magnetic field in addition to this current here. They're all going to be creating magnetic fields, and they're all going to be added up to each other. So it's kind of an unholy mess. And so how do we actually sort of figure this out? And for that purpose, the most straightforward way of figuring it out, which tells you pretty much where all the currents are, is current source density. And so before we talk about sort of the localization of EEG from the scalp, the first thing we're going to talk about is current source density, because that's kind of like the baseline ground truth of where all the currents are. But in order to understand the current source density, then we have to do GradDivCurl. And div is going to be important or divergence is going to be important for understanding the current source density, and curl is going to be important for understanding how we would calculate the magnetic fields. So these are things that would normally be taught in a semester-long electricity and magnetism course, which I would not be capable of teaching. But it's a useful. They're useful in other walks of life, especially gradient. So let's start off with gradient. So gradient. So when we look at gradient, what is the first thing that happens? So the first thing that happens is it's this symbol. And I know when I look at that symbol, it slightly strikes fear into my heart. It's just like, what is that? It's like an upside down delta. It's a Greek letter, and not only that, it's upside down. That's even worse. So this, you can think of this as basically sort of a generalized derivative. So the regular derivative is you just have, a graph of something. And the regular derivative is just at a point, just figure out what the slope is. So what is the rate of change at a point? So the generalized derivative, gradient, is just, or directional, sometimes it's called directional derivative. is just the rate of change when you've got more dimensions. And so what this does, it's a direction. And so what it does is it's going to turn a field of numbers into a field of arrows. So that's fundamentally what it does. So what it does is so when we take this gradient operator, so it operates, it's an operation that's applied to a function. So here's the function, it's a scalar function, but the scalar function is defined at all these 3D points. And so this R here just is a convenient way of writing x, y, z. So that's a vector. X, y, z, the three coordinates of that vector is the R vector. But at each point, at each x, y, z point, there's just a number. So this guy is just so this whole thing is a scalar. That's just a number. So what that means is, so what does this part of it mean? This part of it means you've just got a volume of numbers. So at each point in the volume, there's a number. And what this thing does is, this operator, the gradient operator, is it turns nums into vectors. So now, after you've done this operation, which we're going to describe over here, what you'll end up with is a whole volume of vectors. So at each point in the volume, there's a vector. And so the way this operation works is, we just take the partial derivative, which means let's just pay attention to how this scalar function changes in the x direction. So that's, just tell me how this, if I go a small distance in the x direction, what happens? And we'll make a drawing over here of what's going on. So imagine we've got, that's a little too big because I need 3 of them. So imagine we've got let's just do it discretely, a bunch of little grid cells. So here's, and we'll use the size of the circle to indicate. So here's some grid cells like this. So we use the size of the circle to indicate the size of the scalar at that point. I'm only doing it in 2D, but in reality it's 3D, but we'll just draw it in 2D. So what this one means, this one means is that's the difference between those two. So this is basically the difference in that value as you go in the x direction. So in that case, it got bigger. So that's a positive number. So this thing is a number. And then we have the same thing, here's the change in the scalar field as you move in the y direction. And it got smaller in the y direction. So, but then there's one last thing, critical thing. This is multiplied by the x unit vector. So that's how we get the vector out of it, because this thing is just a number. This just says how much did the scalar field change in the x direction, but now we're multiplying it by the x unit vector. And so now we have a vector in the x direction of a certain length. The length is determined by this guy. So this guy is just a, change in s in x direction. That's a number. And so then to finish the gradient, we have to sort of look at the change in s as you go in the y direction, multiplied by the y unit vector, plus the change in s as you go in the x direction, in the z direction, multiplied by the z unit vector. So what's the multiplying by the unit vector business doing? So let's just sort of work it out here. So what this says is, at this point, the gradient is going to be basically the x unit vector. So here's the x unit vector, length 1. So that's our I. That's our I vector. And then here's the I vector, and here's the j vector. We have to do it three dimensions, but let's just do 2 for now. So that's these guys, the I and j and the k. So now we have to multiply that vector by this thing, and that thing is just the difference between these two. And so say this got twice as big. So that means we have to multiply that vector times 2. So here's, I'll make it dotted so it's a different vector. So here's this term. So this term said we expanded by 2 and then we multiplied by unit vector, so we have like a unit vector that's too long. So now we go and do this one. And so this one says, what happened here? Well, what happened here is it got smaller. So say it went to 0.5 of this one. So this one is twice as big, this one is 0.5. So in that case, we have to multiply by, so this guy would be a negative number, and so we would multiply this guy times a little negative number. We would multiply the j vector by a negative number, 0.5, and then we would get that. And then we just do a vector sum. And so when we do the vector sum, we get, that would give, we'd tip to tail, we'll get this vector. So that vector is that's our gradient. And what does the gradient mean? What's the meaning of the gradient? Well, it's just the steepest uphill direction in this field of numbers. And we're estimating it just by doing sort of x and y. It sort of seems, at first it seems like you're cheating somehow, because shouldn't you check all the different directions to find out which one is the steepest uphill? But this will say, if you want to go the steepest uphill, the fastest change, it's going to be mostly in the x direction and a little bit in the y direction. And it's negative because this guy actually got smaller, whereas this one got bigger. So that's just another way of saying, if you look at it in 2D, so say you have x and y and s going this way, and you have some little surface, the value of s. What is the gradient at each point? It's just go here and just figure out which is the steepest uphill. So this is the way of figuring it out. You just take local differences in the x, y, z direction, multiply them by the vectors, the unit vectors, add all those things together, vector sum, vector sum, and then you get the final vector. So that's the gradient. So that's a real basic one. It's basically just a generalized derivative. Turns a field of numbers into a field of vectors. Okay, so that was good. That was straightforward. So let's move on. So the next one is, so this one's sometimes called just grad, or sometimes del, sort of like for delta, even though it's an upside down delta. So the next one's a little more complicated. It's kind of like a dot product. And so this one is called divergence, or div, divergence. And this one, it's usually written as that del dot, but that all sticks together into a single thing. So here's that one. So that's del dot. So that thing is, you should think of that as one thing. And now this one operates on vectors. So vectors at each point. So this is how we write vectors at each point. So there's a vector function that has, so there's an arrow, some three-dimensional arrow at each point. Here's each point. And now we're doing something to it. We're operating on it with this thing. And so what this thing does, it does the reverse of that. It turns vectors into nums. And so this one is equal to the x component of the vector at a point. That's what that Vx means. Moving in the x direction. So that means, so what does that mean in words? So what that means is change in x component of v. So v is a vector. Let me get that a little out of the way. Change of v in x direction. So we'll write out what that looks like over here. So we got the same sort of grid again. So here's a zooming way in. So we've got a grid, and so say we've got a vector at this point, and a vector at this point, and a vector at this point. Okay, so we can divide each of those vectors. It's in 3D, but we'll just do it in 2D. So we can divide each of those vectors into their x and y components. So here's their x and y components. And then what do? We have to sort of do this one. So this one is the change in the x component of the vector moving in the x direction. So that means just take this thing and compare it to that. What's the difference between those two? So that's our, the x component of that at this point in space moving in the x direction. And so then we just add that to the change in the y component of the vector as you go in the y direction, and add it to the change in the z component of the vector as you go in the z direction. So this one's a little bit like you can sort of think of this one like a dot product in a way, because it's adding up. Remember, a dot product just gives you a number. So it's adding up sort of like, the y component in the y direction with the z component in the z direction. That's kind of a dot product like thing where you multiply x times x plus y times y plus z times z. So that's why it's got a dot there. So what does that measure? So what that measures is basically kind of how radiating are the vectors. So this guy measures. So we have to have words here. So this guy measures, steepest uphill direction. That's what that does. This guy measures, how radiating are vectors at a point. That's what it measures. So if you've got something that looks like this, that has a big divergence. If you run this calculation on something that looks like that, that will have a big divergence. If you have something that looks like this, where they're sort of going in, that will have a negative divergence. And if you have something that looks like it's going around in a circle, that will have a 0. So this is, neg, positive, this is 0. So what this measures, this is a way of measuring, you've got a vector field, and this is what we want to know in terms of current source density. Is there current sort of erupting out, sort of in this radiating pattern at a point, or is the current sort of disappearing into the void at a point, or is it doing neither? It's just sort of going around in circles, in which case it's not erupting or disappearing. So that's the divergence. So it's an intuitive. It was originally developed for like fluid dynamics, like if you imagine sort of like fluid gushing out of a pipe, to sort of, or gushing out of a little hole, sort of appearing out of no place. So that's divergence. So how radiating is a vector field at each point. So this is you calculate this, and it's a single number. It's not a vector. It just says like, is it radiating, sort of like, or just disappearing into the void, or neither? Okay, and then last but not least, we have to do curl. So curl is related to the magnetic field, and when we talk about, so curl, pretty much, you can sort of imagine, what curl is. Curl is just something that's more like a cross product. So here, curl is the worst one in terms of the total number of things there, but it's written like that. And you should think of that as the whole thing. So this is the whole thing. And this one turns vectors into vectors, other vectors into other vectors. And so this is a cross product like. So this one was kind of a dot product like operation where we sort of do, x against x, y against y, z against z. This one is a cross product. So remember the cross product, you're sort of mixing x and y and z. And so when we operate this guy on, this guy operates on a vector field, just like this one does. But the result is we get another field of vectors. And so what does this one look like? So let's quickly draw out the mess here. I'll just give you an example of one of the. So this one is more complicated. So basically it's the change in the z component of the vector at a point when you move in the y direction minus the change in the y component when you move in the z direction, all multiplied by the x direction. So you can see we've mixed up z, y, and then this is the unit vector in the x direction. And then we've got the other one. So I'll draw out the last one because the last one is in a plane. So here's the movement. If we just look at the x component, moving in the z direction, and then we subtract off looking at the z component when we move in the x direction, all multiplied by the y direction. J. And then finally, the one I'll illustrate, which is the change in the y direction when we move in x minus the change in the x component of the vector when we move in the y direction times the z direction. So what is this one in this kind of diagram? So this one kind of essentially just measures how rotating is the vector field. So here's some cheat sheet for me for the vectors, and we'll make a grid on that. Okay, so now we've got a vector, say like that, and this guy is going to be sort of like that, and then this guy is going to be more vertical like that. Okay, so now, so how do we? Let's just do this guy. So here I did. I showed you just these two, and here I just showed you these two. Here I'm just showing you the third one. So what this says is, so here's the components of those vectors, the x and y component. So this one says if we look at the y component of the vector, so the vertical one here, moving in the x direction. So that means here's the y component. So if we compare this guy to this guy, that would be the change in the y component of the vector when you move in the x direction. And then similarly, you would have the change in the x component here as you move in the y direction. Okay, then we subtract those two, and then we multiply by this vector. And remember, the k vector is going to be coming out at you. So this is the k vector. It's coming out of the plane.
I'm going to wrap it up and ask some questions, and I'll see if he's good.
Okay, just 2 more minutes, 1 more minute, yeah. Okay, so what does this do? So to summarize this one, so this measures the kind of circulatoriness of vectors at a point. And so if they're perfectly circulating around, there'll be a big curl and no divergence. If they're perfectly radiating, there'll be a big divergence and no curl. And so this one, you need this one in order to calculate magnetic fields, because you will take the curl of how the currents are flowing, or you can do it the other way around. You can start at the magnetic fields and look at where you expect the electrical currents to be. And so you'll need this thing, and because it's got this cross product like effect, it's going to create something that's kind of at right angles. So that's the curl, the last of the curl. So hopefully this was sort of understandable. Again, you can do, eventually what happens is you work with equations just with these things, and you don't deal with all this stuff. That's just sort of like the details, and we just sort of say, well, we take the curl of something and we know what that means. It means this, but we don't have to worry about it. We think about it at this higher level. So that's really the value of learning this, is that you can sort of think at a more global level about how these complicated coordinates are dealing with each other. So hopefully that wasn't too bad. There's not time for questions this time, but I will leave a good amount of time for questions next time. Okay, David.
All right, thank you.
Okay, see you guys.